Hello everyone, I'm glad to present our latest work on behalf of all the co-authors. It's about the reconstruction of magnetic resonance images in K-space. Magnetic resonance imaging is a medical imaging technology that uses a magnetic field and computer-generated radio waves to generate detailed images of organs and tissues in one's body. It has many advantages. For example, it uses non-ionizing radiation and thus shows no exposure-related harm to the patient. Besides, it can provide better contrast in images of soft tissues compared with CT. It has thus become the primary diagnostic investigation for many clinical problems. However, a long-existing problem is its long acquisition time, which is discomfortable for patients and may cause additional artifacts to the patient or physiological motions. Different from the acquisition of natural images, MR data is first sampled in K-space and then transferred to images. K-space is an array of numbers representing spatial frequency in the MR image. Each point in K-space maps to every point in the image, and vice versa, just like the relationship between frequency and image domain. Sampling in K-space is time-consuming, so we usually undersample the data for acceleration. However, the incomplete sampling will introduce artifacts to the image. So, we need a reconstruction algorithm to recover better quality of the undersampled MRI data. Traditional reconstruction algorithms are based on compressive sensing, but they need complex handcrafted parameter tuning and long process time. In recent years, deep learning-based methods have become the mainstream. Most works would transfer MR data to image domain and apply de-aliasing. Thanks to the great success of computer vision, this kind of algorithm has been well researched for years. By contrast, another school of thinking recognized the potentials of K-space reconstruction and tried to complete the data directly in K-space. However, they still follow the convention in image domain and based algorithms on convolution networks. The reconstruction quality tends to be far from satisfactory. Our hypothesis is the unsuitable inductive bias of CNN leads to poor K-space reconstruction quality. First, naive convolution networks is translation equivariance, but the same value appears in different positions of K-space spectrogram represent totally different information. Besides, the spatial locality leads to limited receptive field, makes it hard to model the long-distance relationship between different K-space points. So we wonder, is it possible to achieve high-quality reconstruction directly in K-space, and what architecture can capture the suitable inductive bias of K-space signal? This leads to the first key idea of this work. We propose a novel transformer-based architecture for K-space learning. It can be divided into an encoder and a decoder. For the encoder, we encode all the sample points by their positions and observed values. And the encoder will model the relationship between all the sampled K-space points and learn a compact representation of the whole K-space spectrogram. In the decoder, we query the encoder's output with the positions of all the unsampled points and generate predictions to complete the spectrogram. We call this procedure as K-space decoding. However, we found that updating a point in the K-space would affect the whole image and will disregard some important spatial bias. For example, MRIs of the same organ tend to be roughly aligned. This inspired us to add a refinement module that converts the K-space reconstruction to image domain for further refinement. We alternate K-space decoding and image refinement to form a basic decoder layer. Compared with previous convolutional-based approaches, our method explicitly encodes the position information of K-space points and enables the network to model the relationship between any 2 points, regardless of their distance. To sum up, the K-space transformer we propose eventually learns a function mapping position coordinates to K-space values, conditioned on sampled ones. This is actually the second key idea of this work, implicit neural representation of the K-space. In this way, we are able to control the resolution of reconstruction by changing the density of query positions. It allows us to design a more flexible decoder. Recall that under a standard decoder, we need to perform self-attention between unsampled points, which is hardly affordable when the sampling ratio is very low, and that is often the case in practice. We thus design a hierarchical decoder that consists of a high-resolution decoder and a low-resolution decoder. The low-resolution decoder reconstructs the K-space spectrogram in a lower resolution, serving as a bottleneck, and the high-resolution decoder refines the result in original resolution but discards the self-attention module. In this way, we can achieve a balance between performance and efficiency. We now demonstrate some experiment results. We conduct experiments on two public MRI datasets, oil spring MRI dataset and fast MRI knee dataset. To generate training and test data, we randomly masked the fully sampled K-space data to simulate the undersampling process. Follow the convention of previous works. We consider Gaussian 2D sampling pattern and uniform 1D sampling pattern, and we consider three different acceleration ratios. Here, we define the acceleration ratio as reciprocal of the sampling ratio. For example, if we only sample 20% of the odd points, then the acceleration ratio will be 5 times. We evaluate all the methods with PSNR and structure similarity as the matrix. As can be seen from the tables, our method achieved the best on 15 out of 18 results and demonstrates superior or comparable performance to the current state of the art. We also include the K-space unit for comparison, which show very poor performance and justify our hypothesis that CNN do not give suitable inductive bias for K-space learning. Here, we show more visualization results under the uniform 1D sampling 5 times acceleration. The first row are input, ground truth data, and reconstruction results of different methods. The second row are undersampling trajectory and error maps. Here, brighter means higher error. As can be seen on both spring and knee datasets, our method recovers small anatomical details and shows the best reconstruction quality. Due to time limits, we will not demonstrate all the experiment results here. For more details, we would like you to refer to our paper and supplementary materials. That's all for our presentation. Thanks for your listening.